Kim Buckley, and I'm a member of the Science, Medicine, and Technology Committee. And it's my pleasure this afternoon to introduce Kristen Renkema. Kristen is an assistant professor in the Biomedical Sciences Department at Grand Valley State University. She received a BA in Biology and Writing at Anderson University and completed her PhD in Immunobiology at the University of Arizona. She did her postdoc work at the University of Minnesota. And Kristen is a native of West Michigan. So without further ado, Kristen, I'll turn it over to you.
Thank you very much for that introduction. It is my pleasure to be here with all of you virtually. I really wish that I could be here with you in person, but who knows, maybe stay tuned, maybe in the future we'll be able to do that for a future lecture. So what I want to, and let me mention too, as I'm getting my presentation up, in terms of questions, I have absolutely no problem if people want to ask questions kind of in the middle of the presentation. It's easiest for me if you either write your question in the chat function or you give me a little like, I have a question in the chat function. That way I know to stop, because I look at that periodically, and either unmute you or I can answer your question directly from what's typed on the chat. I also will try to here and there take a breath and pause and give time for questions, periodically throughout the presentation as well. If that's an easier way to step in and give questions. And of course, there'll be hopefully time for discussion after the presentation's over as well. Can I get a thumbs up if you can hear me? Just want to make sure. Yeah, awesome, thank you. It's just disconcerting. It is very disconcerting to do this sometimes and be like, I think I'm talking, but maybe I'm dreaming, I don't know. So I am going to do a typical scientist presentation, and that's going to be using PowerPoint. Hopefully not too many words on there for you. So hopefully at this point you are seeing on your screen a PowerPoint with a title slide. I'm seeing some nods, so I'm gonna, yeah, thumbs up, awesome. So, and I have the chat function up on my screen as well. So if you type something to me, I should be able to see it. All right. So as an immunologist, I have always been interested in how the cells of the immune system communicate with one another and work together to form an intricate and beautiful immune response, basically against anything that you can throw at the immune system. And so that's my primary passion, is understanding how that works, and if there are ways through our understanding to be able to help the immune system do it even better. So one of the ways that is one of the greatest triumphs in immunology, as well as in medicine in general, is vaccination. And so I'm going to talk to you today briefly about what the immune system actually does and how these really cool different cell types work together, and then how we take advantage of what happens naturally in the process of vaccination. So that's where we're going with this presentation. Maybe, there it goes. All right, so first of all, just some general goals of the immune system. I always start out an immunology course or an immunology lecture with a slide like this, just to remind everyone what you already pretty much know, is what the goals, the main goals, the big picture goals of the immune system actually are. So the first goal of the immune system is to be able to recognize danger. So there are a lot of things in our bodies that technically the immune system can recognize, but we don't want it to recognize our own bodies or something that's not particularly dangerous for our bodies. We only want the immune system to recognize true dangers or true threats. And that's actually an extremely intricate process that we are still learning more and more about. So that's number one. Number two, once that danger is recognized as actually potentially dangerous, the immune system wants to both contain and hopefully fully eliminate that danger. The immune system doesn't always get it right, doesn't always complete these two items, but theoretically, that is what we want for the immune system. Also important, thirdly, and one that's often forgotten, is we want the immune system to turn off when the danger is actually gone. Think about it. So what if you had a cold and your immune system reacted and eliminated the virus that caused that cold, but then didn't actually ever turn off? It stayed activated. You think that'd be a good thing? Probably not, right? So this is actually how you can get some autoimmune type disorders, is if the immune system does not turn off appropriately, you can start damaging the body. And then finally, and very important to vaccination, the immune system is capable of making memory, which we will talk about in more detail in a moment. All right, so where are we going next? We're going to talk about how this actually happens. So I would be remiss as an immunologist if I did not mention what we call the first line of defense. And it's often not even included in immunology textbooks, which makes me sad, but I think it's really important. And it's this first line of defense that really its main goal is to prevent infection from taking hold. So I broke it down to kind of three main pieces. The first being the skin. So that's what this top right picture is. It's actually a blown up picture of the epidermis. So the top layer of the skin. That top layer of the skin, the top layer of the epidermis, is made of dead skin cells. And those dead skin cells have a lot of keratin in it. Keratin might sound familiar to you. It's what's the main component of like our fingernails and our hair. It's very tough. So if you have an intact epidermis skin layer, that is basically an impenetrable barrier to potential dangers. And as you know, the skin covers our entire body. So it's really to protect us against fluid loss and other important things. But one of the main function of skin is to prevent against infection. The other first line of defense are the mucous membranes. So what about the parts of our bodies that still can come in contact with the outside world, but don't have skin anymore? So these would be things like the respiratory tract, the urinary tract, the digestive tract, the reproductive tract, basically anything that's being allowed to get inside our bodies that don't have skin protection, they are protected by mucous membranes. And that's what this middle picture is showing, the kind of pinkish picture on the screen. So there is a thick layer of mucus that lies on top of the cells here. You can't really see it in this picture. I couldn't really find a great picture of it. And that mucus itself is actually very difficult for viruses and bacteria in particular to penetrate. So even if you inhale, let's say a cold virus, into your respiratory tract, that virus is actually going to have a kind of difficult time penetrating the mucus that's already there coating that surface. We also have cilia, which are tiny little protrusions. They look like little hairs, basically, that sit on top of the cells that line our mucous membranes. And those cilia beat like this. And so you can imagine all these little hairs on top of the cells beating in emotion. So they're moving that mucus, and they're moving anything that's potentially stuck in that mucus away from our bodies, and eventually usually is coughed up. So it's a really cool system that's really important to preventing infection. Finally, I'm not going to go in a lot of detail about this, but there are lots of enzymes and chemicals that are present in this first line of defense that also help prevent against infection. So just for an example, sweat, for instance. Sweat is acidic and it's also moving on the skin, which can help prevent infection. There are certain enzymes in our tears that can actually chop up certain bacteria. There are tons and tons and tons of these, and they're still being discovered actually. So this first line of defense is really important to preventing infection from happening. But that is not where we will be spending our time. We're going to talk about the actual immune response. So you're going to be seeing this graph a lot during my presentation. In fact, you will probably get sick of seeing it, but I don't want to know that. Just pretend you like seeing it. So on this graph, what we have is we have just number axis here. Hopefully you can see my little pointer, but this is the y-axis going upwards. That's number or magnitude. And then on the x-axis, which is the bottom axis, is time. And we'll leave it at that. We're not going to get more specific. And then we have our little person here. So first term jargon, so to speak, of immunology that some of you may have heard of before is the term pathogen. What I mean by pathogen is I mean an infectious agent that is capable of causing disease. So a bacteria could be a pathogen. Virus could be a pathogen. SARS-CoV-2 is a pathogen. These are all there's like a lumped together term that we can use for that dangerous agent that I was speaking of earlier. I'm going to use the word pathogen for that. So let's say we've got a pathogen, probably either a virus or a bacteria in this case. Usually you don't get co-infected, although sometimes that does happen. And let's say that that particular pathogen overcomes that first line. So let's say I have a cut that now breaks my skin open. That means a pathogen can enter and get through that line of defense. Let's say I inhale a virus into my respiratory tract and it gets through the mucus. It is now broken through that first line of defense. So what happens next? So what happens is that the pathogens, their main goals are to replicate, so make more of themselves inside of the host, and then eventually get out and infect something else. That's really the main goal of a pathogen. So what happens is this pathogen starts to replicate in your body. And so as they replicate, they are making more of themselves. So they start increasing on this scale. That's why they're going up. There are more and more of these pathogens now in our body. So the first thing to respond, and oh, sorry, that means that there is now a danger signal that is going to be sensed, hopefully, by the immune system. So this is where we get to that complex network of cells. So in the immune system, the cells of the immune system are generally called white blood cells, WBC, if you've seen that on a CBC count or anything like that. White blood cells basically are the cells of the immune system, at least in the blood. Now, that name is misleading because there's lots of different kinds of white blood cells, and we'll talk about some of them more specifically in a minute. But this is now at the stage of the game where the white blood cells of the immune system are going to start getting involved. So if we plot, so to speak, on the same graph here, the immune system, it's really cool because as these pathogens are sensed as dangerous, the immune system also starts to replicate itself, starts to divide cellularly in order to increase their numbers as well, in order to fight this epic battle. So basically, you've got the pathogen army being built, and you also have the immune system army being built. The first thing we're going to talk about is what I like to call the second line of defense. Remember, the first line were those barriers. Now the second line is the innate immune system. The innate immune system responds rapidly to an ongoing threat in the body. Good so far? Anybody have any comments, questions? I'm going to talk about some of those cells now specifically. Okay, well, feel free to send a chat if you have a question. Oh, it doesn't like when I use certain keys on my keyboard to try to move the screen. Okay, so white blood cells. We often just talk about, oh, white blood cells versus red blood cells in the blood. But like I already mentioned, there are actually a lot of different types of white blood cells. And so what I included here, this is actually straight out of the immunology textbook I used at Grand Valley. This is a blood smear where they've taken human blood and put it on a slide and stained it certain ways so you can see it under the microscope. And then they focused in and looked at different types of these immune cells. So these are all white blood cells, but they're very different from one another. So there are two on the top here called basophils and eosinophils. Basophils, if you have seasonal allergies, these are the main implicator of seasonal allergy. They degranulate, they release tons of histamine. So if you've got allergies, like seasonal allergies, chances are you probably have a larger number of these basophils. They're actually usually quite rare. They're the rarest type of white blood cell, usually. Eosinophils, we think, were originally there to fight against parasitic worm infections. But since in the developed world, we don't really have a lot of those types of infections anymore. Eosinophils are more commonly found to be involved with chronic allergies. So eosinophils are huge players in terms of chronic asthma. So these two cell types are really interesting, and especially interesting to me with what I research personally, but we're not going to spend a lot of time with them today. We are going to talk a little bit about neutrophils, which are the bottom left cells here. Neutrophils are by far the most abundant white blood cell in the blood. We'll talk more about them in a minute. We have monocytes, which are right here on the bottom right. And there will be two cell types that would be classified as monocytes called macrophages and dendritic cells. Don't worry, we will talk more about these. You'll see these words again, no worries. And then finally, the lymphocytes, which are actually part of the adaptive immune system, which is the third line of defense. So right now we're on the second line of defense. So what we're going to talk about now is we're going to talk a little bit more about neutrophils, macrophages, and dendritic cells, what they are, what they do, and why they're important. Okay. Maybe. All right, I told you you're going to see this graph last. So it's the same one that you saw before, where we have pathogens increasing, and we also have the immune system rising to the challenge and increasing as well. And the first arm, so to speak, or branch of the immune system that responds to an infection is the innate immune system. So macrophages, one of those innate immune cells. These are some of my most favorite cells ever because they're really, really cool. I like to call these cells the garbage collectors of the immune system. So what they do is they go around and they are typically guarding all the barrier surfaces. So all underneath your skin, there are macrophages just lining that. Same thing with mucous membranes. You've got macrophages just lining those surfaces. So these macrophages are usually the first cell to realize, so to speak, that there is an infection happening. And they are the garbage collectors, I like to call them, because even when there's no infection happening, as they just kind of crawl under the surface, they're constantly taking sips of things, just in their environment, grabbing little bits, taking them inside, and seeing what's around there in the environment. In this picture, we have a macrophage that's been activated because it sensed that there's a danger happening, and it's actually extending, this is called a pseudopod. It extends the pseudopod. It almost looks like an amoeba, if you've ever seen an amoeba. And then the little tiny thing that that pseudopod is extending to, that's actually a bacteria. It's using its pseudopod, and what it's going to do, if this is a video, is it would grab hold of that bacteria and draw it back into itself to degrade the bacteria. That special type of, it's actually eating, so to speak, of the pathogen has a special name. It's called phagocytosis. Don't know if you've heard of that before.
Oh,
but phagocytosis is when the cells of the immune system in particular are engulfing and then killing a pathogen. And macrophages are super good at this. So they're one of my favorites. Oh, I pushed the right button. All right, so what's another cell type of the innate immune system? The neutrophil. So remember, the neutrophil makes up between 60 to 70% of the white blood cells in the blood. So it is very abundant. I call neutrophils the foot soldier. There are many of them. They are good at killing, and they are extremely expendable. Sorry, that's probably bad, but for the immune system's sake, the neutrophil is definitely the foot soldier. And so neutrophils are really short-lived. And so if they're activated, they usually get activated by a macrophage. If they get activated, they're just going to pour their little cellular hearts and souls into killing the pathogen, whatever it is. And they are very good killers. So with macrophages, neutrophils have a lot of different types of mechanisms in the way that they can kill. But one of my favorites is actually what's shown in your picture here. So we've got a very, very, very blown up picture of a neutrophil. This is with a special electron scanning microscope that can see so closely, you can actually see strands of DNA. That's how zoomed in this particular microscope can get. So we're zooming into a neutrophil. And so this gray body here, that's the neutrophil right here. And then you see what's been artificially colored as this kind of blue stringy stuff coming through. It looks like silly string to me, I think, personally. What the neutrophil is doing is it's basically sacrificing itself to contain and kill infection. So this neutrophil has basically opened up and spewed its own DNA out in order to try to catch, in this case, bacteria. That DNA is really, really sticky. Not only does it, encode life, but it's also very, very sticky. So it can be used as a weapon if used appropriately. So neutrophils can do this, which I find to be just spectacular. And one of the really cool ways that neutrophils can help to contain infection. Another thing about neutrophils is that they respond really, really rapidly to an site of infection. And so if you've ever had an infected cut or something and you've noticed pus, most people know what pus is. Pus is usually kind of got a whitish color. It's because of all the dead neutrophils. If you were to look under a microscope at that pus, it would be mostly dead neutrophils. So there's a little piece of, information, a little fun icebreaker you can give during a dinner or something. You can talk about what pus really is. I don't know. I probably would work for me, but maybe not for most people. So neutrophils, another innate immune cell that's involved with responding really early in terms of infection. And then finally, the last cell type of the innate immune system I want to talk about actually gets involved a little bit later. So let's say, I don't know if you guys saw that. So let's say the pathogens are overcoming our innate cells. Our macrophages, our neutrophils are doing their very best job, but they are not containing and eliminating the infection by itself. That means we need to start bringing in the other arm of the immune system, which is the adaptive immune system. So imagine that these pathogens continue to replicate, this red line continuing to go up on our graph here. We need to rise to this challenge. And so what creates this actual increase of the immune response is what we'll talk about next. But to get there, we need to talk about a special cell type. So we need to basically go from an innate immediate response to an adaptive immune response. And the really cool thing is that the innate immune response actually activates the adaptive response. So you cannot get an adaptive response unless you have had an innate response. That's something kind of important to keep in mind. So the innate response, responding, initially, basically informs the adaptive response. Hey, there's something dangerous happening here, and we need your help. So the way that the innate response does this is through a really special cell type, and this is called a dendritic cell. It's called a dendritic cell because it has dendrites. That's what these little protrusions are. It kind of looks like a neuron from a brain, if you've ever seen any of those. It's got these dendrites, okay? And this dendritic cell, I call the bridge. It is the bridge between innate and adaptive. You need the dendritic cells to get the adaptive response started. So if we look at this little kind of schematic here, I have my little dendritic cell drawn by my husband because he has patience for that type of thing and I don't. I draw like a stick figure dendritic cell or something. So this is a dendritic cell. It basically can take the pathogen and bring it to the adaptive cells. To inform the adaptive cells, you have to get involved now. So this adaptive response is what we call the third line of defense. All right, same graph here. So the first type of an adaptive cell is called a T cell. And I'm guessing a lot of you have probably heard of the word T cell before, which is exciting to me because T cells are by far my favorite cell in the immune system. I'm allowed to be biased. T cells are the coolest. Let's put it out there. So T cells are actually activated directly by dendritic cells. So just as a reminder, the dendritic cell will be able to take bits and pieces really of the dangerous agent, whatever it is, to the T cell in order to activate it. There are two types of T cells. The first one is called a helper T cell. That's literally what it's called. That's also a really great description. Helper T cells really are like the director of an orchestra. If you think of an orchestra being all the different types of immune cells working together towards a similar goal, the helper T cells direct that through various ways. So they're extremely important. Then we also have a type of T cell. It's called, technically it's called a cytotoxic T cell, but I like to call them assassins. These particular cytotoxic T cells are really great killers, and they do that through a variety of ways. But what they're really, really good at is killing infected host cells. So they're so good at being little assassins that they can go around and detect an infected cell versus a non-infected cell. And even if those two cells are right next to each other, that assassin T cell can kill the infected cell and leave the uninfected cell completely healthy and intact. Very precise. These assassin T cells are actually where I have spent most of my research time. I researched them when I was in graduate school, and then I also researched them when I was in my postdoc. So I definitely am biased, but I think they're the coolest. All right. And then the final cell type, I promise we're almost done with cell types. The finest cell type that I want to bring up is, again, probably one that you've heard of, and that is the B cell. So T cells, which we just talked about, and B cells are the adaptive cells of the immune response. Why do we give them a different kind of characterization? Well, we give that because they take quite a while to get activated, whereas the innate immune response can respond quickly, almost immediately, basically. And the adaptive cells are extremely specific. So kind of beyond the scope of what we want to talk about today, but I'm happy to talk more about kind of what makes an innate cell versus an adaptive cell if you have interest in that later. So B cells become activated, again, through the pathogen, and they are antibody factories. This is what makes antibodies. And I'm sure a lot of you have heard about antibodies, especially recently with COVID-19 and potential therapies coming through. So what are antibodies? Well, there are these little proteins, and they're usually like, they look like little Y-shaped proteins that are secreted by the B cells. And those antibodies are so specific that they can bind whatever the pathogen is. So I've kind of shown a bacteria here coated with antibody and a virus here coated in antibody. This is not to scale. The antibodies would be much, much smaller than the pathogen here. You can picture, let's say you have a virus. Well, you can even go further. Let's say we have the COVID-19 virus. Let's say you have that virus and it's, picture it coated, the whole surface of it is coated with these Y-shaped things. You can probably predict that that virus is not going to be able to easily infect another cell, right? It's basically got this coating all around it. It's kind of a dud at that point. So we have a special name for that type of antibody function, and it's called neutralization. So if you've heard of the term neutralizing antibody, neutralizing antibodies are very good antibodies. That means they work well against a certain pathogen. So if you're producing, your body, your immune system, if you're producing neutralizing antibody against a certain bacteria or virus, that means that you have a much better chance of getting rid of that virus or bacteria. Antibodies have a lot of functions other than the neutralization, but that's the one I think that's been kind of in the news recently. So I thought that's the one I would talk about a little bit more. So antibodies, hallmark of B cells and a hallmark of an adaptive immune response. Okay. So I think this might be the last time I show this. Oh no, just kidding. I'm going to show the graph again, but it'll be a little bit different. All right, so what does this mean, big picture? If the immune response is successful, the pathogens will be contained and eliminated. Remember our goal for the immune response? So back down to zero, they're gone in our bodies. Remember that other goal that we have for the immune system though, is that it too turns off when the threat is gone. So the immune response actually does, it's called contraction, it actually has a term, where after the pathogen is cleared from the body, the immune response also contracts. But here's what's really cool about B cells and T cells in particular. So our B cells and T cells, shown here in our little picture, they can create long-lasting immune memory. So what does that mean? On this graph here, that basically means that you get this protective population of B cells and T cells that are still specific to whatever the initial infection was. And they're basically patrolling the body in case you happen to get reinfected with the same thing. Okay? And they can last, this protective memory can last a lifetime. So let's say you're unlucky and you get reinfected with the same exact thing that you were initially infected with. The pathogen starts to replicate in your body, but because you already have this pre-existing memory population, your immune response flies up so quickly that the pathogen is eliminated even before you know you're sick, usually. And then you will have another period of contraction. So this is usually like the main graph that I want people who take a class with me, like a whole course of immunology. I basically want them to know this as a main takeaway. This is what a typical immune response looks like, simplified in graph form. All right, so I promised vaccination, and that's where we are heading next. But I wanted to kind of share with you what's happening with a normal immune response, because vaccination is using all of these pieces. So it's just much easier to understand what vaccination is if you already know a little bit about what's happening in an immune response in general. Are there any questions about this material before I move on to talk a little bit more about it, but in the context of vaccination? I'm going to use this opportunity to drink some tea.
I have a question. Are these immune responses in any way a part of a person's inheritance from their parents?
That is an excellent question. The genetics of a person will definitely influence their immune responses. So either potentially in really subtle ways, or maybe even in larger ways. So for instance, just as an example, we do know that certain types of allergies and asthma do have a genetic component. And what was found was that that seems to be having a lot to do with those two cell types I mentioned that we weren't going to go over too much more in this talk, which is like basophils and eosinophils. So some people just have more of those cells due to their genes. They just produce more of them. But if you have more of those cells in your body, you are more prone to developing allergies. So if your parents had the certain genes that made them have increased basophils or eosinophils, then you have a stronger likelihood of also inheriting that, if that makes sense. So there definitely are genetic influences on this. A normal human being without major, genetic deficiencies will have all of these components though. So you will have B cells, you will have T cells, unless you have a really big genetic mutation or something like that. Yeah, great question.
Another question that's related. So if you have autoimmune deficiencies, what does that make this look like? Does the blue line not go up? Does it never come down?
Either. It could be either, depending on what we're talking about. So let's say you don't have, so I should say autoimmune and deficiencies are kind of two different things. So deficiency would be an immunodeficiency where you're missing a pretty big component of this. And so like, let's say you don't have T cells. That actually is such a severe autoimmunity that most children will die before the age of 2 if you don't have T cells. Yeah. So it can be really severe like that. Or if you are missing potentially some other type of cell where maybe your immune response would be slightly less, but other cells could make up for it, because there is definitely overlap in some of the functions. And then, so in those types of cases, then on this graph, the blue line would be maybe 0, just depending basically, or maybe slightly lower, but not enough to make a huge difference, that type of thing. It just depends on what's missing or what's lacking. If you have autoimmunity, then it is definitely possible that instead of, can you see my mouse? Oh, great.
Yes.
So instead of it contracting like this, it might stay steady or even start increasing, which is not a good thing. If you've heard of the term immunopathology, where sometimes if you get sick with something, the thing that ends up causing the most damage is actually your own immune system. A lot of times that is due to contraction not happening properly.
Thank you.
Yeah,
May I ask a question, please?
sure.
Why is it that some people, me personally, have a congenital immune deficiency, yet I'm collecting autoimmune conditions constantly? So I receive antibody replacement, IgG, and I take meds, including biologics, to reduce my immune system because of rheumatoid arthritis and several other things. That seems confusing. Plus, I have allergies with low antibodies and neutropenia. So just seems sort of all out of whack. Is that?
Yeah, no, that's, so, I should preface that I am not a medical doctor. Maybe I should have said that first. But from an immunologist standpoint, it seems that depending on what the initial issue is, especially once we start treating with an immunotherapy, that can then push us into another issue. So for instance, if I just kind of pick and choose something that you mentioned, so you get treated with, antibody therapy for one condition. That's actually a really common replacement therapy for certain types of immunodeficiencies. There are many, many immunodeficiencies that will impact the amount of antibody that's made. But the problem is that a lot of autoimmunity is antibody mediated, including rheumatoid arthritis. So if you start increasing the antibodies, especially certain types of antibodies in the body, then those antibodies might be more likely to start binding what they shouldn't be, which is joints in the case of rheumatoid arthritis, and causing a problem. So now, you go down that path. With rheumatoid arthritis, there's a massive amount of inflammation that happens. And inflammation basically can signal to every single immune cell in the body. So then you can also start kind of going on this path of having varying effects. So I'm sorry, that sounds awful. And
Just
from an immunology standpoint, these cells, they're in constant communication with each other and they're sensitive. And so unfortunately, it's not surprising to me that you could indeed experience kind of a cascade of different types of things.
Okay, thank you.
Yeah. I have a question by chat about how do bacteria differ from viruses? That's a great question. Maybe I should have explained that in the beginning. So most biologists would not classify viruses as living. And that is because they are very simple and they require a host cell in order to be able to make more of themselves. So if you just had a virus sitting around on the table, it can't do anything. It cannot make more of itself by itself. But if it gets into me and into my cells, it basically hijacks my cells to make little viral factories for itself. So viruses are very simple, and they're basically like little parasites. Bacteria, on the other hand, they are living. They can do all of those things for themselves. So, and there's some cellular and biological differences as well, but those are the main differences there. Any other questions? Okay.
Yes, I have one.
Sure.
Can you explain why this COVID virus is causing a cytokine storm?
I will get to that question at the end.
Okay, thank you.
Yep. Other ones? I think I'll probably move on just to make sure we get through the other material. I don't want to take up too much of your time. Of course, if you're happy to have me, I'll just stay too. That's cool with me. All right, so we talked about what can happen in a normal immune response in a healthy individual. And it'd be awesome if this happened every single time any of us got sick. But as we all know, that doesn't always happen. So in severe disease, what often happens is that this immune response is not allowed to progress. Okay, so I put a big X and like a red box over what can happen with certain severe diseases. And there's a number of ways why this might happen. So the pathogen, or virus or a bacteria in this case, can overcome the immune response. So you can imagine in our graph that this red line would just keep going and that the blue line couldn't catch up. Okay. Sometimes the pathogen is really mean and will actually directly inhibit or even kill the immune response. There are certain pathogens that will go around and kill T cells or macrophages just to stop the immune response. Also, and this is what actually was just alluded to with the cytokine storm, is that the immune system itself causes so much damage that the patient really suffers. And there's numerous reasons why that might happen. The one I'm going to focus on right now are these first two, because smallpox is a virus that was really very, very good at overcoming the immune response and causing extremely severe disease. And it's very important for understanding the history of vaccination. So smallpox is caused by a virus. So that means that it needs a host cell in order to actually replicate. And this is a picture, a close-up picture of one little viral particle of smallpox. It's highly, highly contagious. And it had a 30% mortality rate. So if you got smallpox, you had a 30% chance of dying, which is huge. It's a huge mortality rate. Prior to the vaccine, the WHO estimates that about 300 million people died just in the 20th century from smallpox. Then came along this guy named Edward Jenner. He was a physician in England, and he started noticing that milkmaids would contract kind of a very mild case of what looked like smallpox. And they ended up calling that disease cowpox. And he also noticed that milkmaids that had cowpox at some point would not contract smallpox. So he had really quite questionable ethics and did an experiment that he probably shouldn't have. And what he did is he actually took pus from a cowpox pustule from a milkmaid and inoculated, so purposefully infected a young boy with that. He waited a little while, and then he purposefully exposed that boy to smallpox. Remember, 30% chance mortality. That boy did not develop smallpox. And therefore, the field of vaccination was born. So we now know that cowpox is actually vaccinia virus, and that is where the word vaccination comes from. Vaccinia virus vaccination describes this original setup with cowpox protecting against smallpox infection. So since this questionable experiment, there have been many different versions of the smallpox vaccine. The WHO mounted a really successful and quite aggressive vaccination campaign in the mid-1900s, and smallpox was declared completely eradicated worldwide in 1980. And vaccination has discontinued for regular populations. So at this point, a lot of people don't know this, but there still is smallpox virus that exists in labs. It is only in 2 places in the world that we know of, at least. One of them is in the CDC in Atlanta. One of them is in Russia. Otherwise, smallpox stores and virus should be completely destroyed. And those are like in deep freeze. So the other thing that Edward Jenner did is he's actually called the father of immunology, because he opened up this whole new avenue of science with his questionable experiments, because not only was it cool that this little boy was protected against smallpox, but it also, you know, came up with the question of why, right? Why was this young boy protected? And we now know that's because of the immune system. All right, so vaccine logic. Let's say this green line on this graph that you're used to seeing is a vaccine now, where I inject someone with a vaccine, okay? There are 4 main types of vaccines that are given currently in the US. The first one is called the inactivated whole, which I'll show you a picture in a second. And now the second one is called inactivated subunit. And third one is called a toxoid. So basically what this means for you is I take a virus, I inactivate it, which basically means kill it completely. I break it all apart into little pieces. I purify either some of those pieces or all of those pieces, and that's what becomes my vaccine. Okay? So, for example, influenza, the flu vaccine, is a purified few number of proteins that originated from the virus. It is not the whole virus. It is little bits and pieces of it completely broken apart. So if anyone ever tells you, I got the flu from the influenza vaccine, that is literally impossible. Impossible. Because all we're doing is we're injecting a few little pieces purified from that virus. There's no way that that can create flu, just so you know. Another little tidbit, along with the neutrophils and pus thing that you can take away from this. So if I give a person one of these vaccines, it doesn't actually end up replicating. It just kind of stays steady for a little bit. These things aren't alive. They're dead and broken up. But hopefully, we're still going to get an immune response. We're tricking the immune system to thinking that that pathogen is there, even though we're only giving it little bits and pieces of it. We still get, hopefully, an innate and adaptive immune response with contraction and immune memory. You can probably see where I'm going here, right? So hopefully at this point, we've got protective immune memory cells. Now let's say I happen to get infected with a real pathogen. So let's say I get the flu vaccine and later on I get infected with a flu that I happen to be vaccinated against. You can imagine what's going to happen here, right? We're going to get a massive immune response because our memory cells, that's what they're there for. The real flu or whatever it is gets taken care of so quickly, we never knew we were sick. This is what a vaccine is. It's not scary. It's just making an immune response. Hopefully an initial immune response that doesn't have a 30% mortality rate, right? Some of these types of vaccines here are really wimpy. And the immune response is like, I'm not going to react against you. You're just a little piece of protein. Why would I care? In those cases, it might be necessary to use an adjuvant in the vaccine. And adjuvants are usually trying to create a little bit of inflammation or try to trick the immune response into thinking that, oh, I actually do need to respond against that. So I have a question about if people say they got sick from the flu vaccine, is it a different pathogen or something else? Excellent question, and it definitely could be a different pathogen. If you think about when flu season is and people are getting their flu vaccines, usually right before flu season, there's usually a lot of other seasonal bugs happening. So it often is thought to be just sick from something else. The flu vaccine can cause some mild inflammation and swelling, and in some people, a mild fever, just because think about what we're doing, right? We're trying to make an immune response here. So sometimes people will assume that a slight reaction to the flu vaccine itself is full-blown flu, even though it has absolutely no like respiratory symptoms. So yeah, it's probably not the same for everybody, but those would be the two most likely reason why people think that they get sick from the vaccine. Okay. So it's 2 o'clock now. I just want to make sure I'm not taking up too much of your time because I'm pretty good at like wrapping things up quickly if needed. Do I have till 2:30? But that includes with discussion, right?
Yeah, you can. You've got at least a good half hour, and I like your ideas. If people, want to hang in there while you answer questions,
okay,
that's allowed too.
Great. Yeah, and I won't be offended if you have to duck out too.
Oh, I'm good. This is fascinating stuff.
Yeah, this is great. Thank you so much. So what's happening?
Those things cannot replicate. They are just bits and pieces. There is a type of vaccine called an attenuated vaccine. So in an attenuated vaccine, this is actually a live bug, okay? And then the MMR vaccine, the measles, mumps, and rubella vaccine, those are all attenuated. So what does that mean? Basically, we take the virus or the bacteria, whatever we're using, and we modify it to make it super wimpy, okay? So actually cowpox would be an example of an attenuated virus. It happened naturally, but it was super wimpy in humans. Luckily though, the immune response that happens against cowpox also protects against smallpox. So an attenuated is a highly modified virus or bacteria. And so again, in green here, here's my vaccine that I'm giving. These can do limited numbers of replications. So they might increase slightly in the human initially. And once again, you're gonna hopefully get a nice immune response that looks like a normal immune response against this attenuated pathogen. You get reinfected, once again, really strong memory immune response that takes care of that bug before you get sick. Okay. All right, so those are what vaccines actually are and the logic behind using them. As an immunologist and as a scientist, at least to me, the logic behind the design makes sense to me. So this is a graph that actually shows something I already mentioned. and that is that memory cells can be protective for many years. They did a really good job about following people who received the smallpox vaccination. And there are ways that you can look in the blood and detect whether antibodies are still there. And what they found was, even, this graph is actually outdated, it's more than 80 years, even 80 years post-vaccination, there were protected neutralizing antibody against smallpox. So not all vaccines are this good. There's still a lot of science out there to try to improve the vaccine technology, but this is possible. I have another message about what message do you have for people who are against vaccines. We'll get there. Hold on. All right. So from now on, my last bit of this talk is going to be less of the science stuff and just more about like how are vaccines actually developed and tested, and what are our considerations. Okay. So the first thing is that most vaccines take at least 15 years of science and phase trials before they are released to the general public. Most. In fact, the ones that are in the market today did indeed go between 10 to 15 years plus of testing. So what that means is, first, original scientific studies have to be done to develop a potential vaccine candidate. Then you have to convince the FDA to get you approval to do clinical trials. Then you start clinical trials. I can talk more about phase 1 and phase 2 and phase 3 clinical trials in a little bit if you're interested, but they're stepwise and highly regulated. Vaccines actually go into a phase 4 clinical trial, which basically means that in the entire lifetime that the vaccine is used in the clinic, they are highly monitored and data is collected. Memory cells are B and T cells. Both B and T cells, Kathy, both B and T cells can become memory. During this phase 4, there's a special reporting system that's in place, and I'll talk more about that in just a second. So you'll see that acronym again, the VAERS, V-A-E-R-S. And the thing that I find people are most scared of in terms of vaccines is what's actually in the vial, like what are we actually injecting our kids with? And I get that. I mean, I first want to say that I'm super empathetic. I have 2 small children, so I also don't want to be injecting my kids with poison, at least most days. So these common components of vaccines are fluid. To make it fluid, it's usually sterile water. There's some preservatives and stabilizers sometimes in there, because if you think about it, sometimes these vaccines have to travel a long way. And so we want to keep them as stable as possible. I'll talk more about that in a second. Adjuvants, right? We talked about adjuvants, how sometimes those are necessary to help trick the immune system into responding. And then depending on the vaccine, there can be trace amounts from how they're prepared, which I'll give you an example of on the next slide. So these vaccine components, like I said, this is really where I see a lot of hesitation is, these components that are in the vaccine, are they harmful? And I just usually tell people that who are worried about this is, there's a lot of science that goes behind choosing these particular components, as well as testing for safety. When a vaccine goes through clinical trials, not only are we testing to make sure it works and is worthwhile, but we're also putting it through the ringer in terms of safety as well. So one of the things that's commonly found in vaccines in the United States is aluminum salts. You may have heard of this. This is used as an adjuvant, actually. It's actually really good at stimulating macrophages. Aluminum is one of the most common elements on Earth. And in terms of the amounts of aluminum that are in vaccines, it's good to put it in perspective. So in the first 6 months of life, an infant, if it is on the normal vaccination schedule, will receive about 4.4 milligrams of aluminum cumulative over all of those vaccines. And that same first 6 months of life, if that infant is breastfed, it will get 7 milligrams of aluminum just from the breast milk. If that infant is formula fed, it will receive 38 milligrams of aluminum in the formula. Formula is also highly tested for safety and put through the ringer. So it's just important sometimes to kind of keep things in perspective. Yes, if you ingest way too much aluminum, are you going to get sick? Yes. But that's not what we're talking about here. Formaldehyde. Everyone always like, ooh, formaldehyde, you know. We use it to preserve things, right? So formaldehyde is actually not used as a preservative in vaccines. It's used as an original deactivation agent. So you remember way back in the picture I showed you where you would have like a virus and we broke it up? It's used in that step. So sometimes you do get a trace amount of formaldehyde left in the vaccine. However, if you take a measurement in infants, they already have 1,500 times the amount of formaldehyde in the blood than what they get in a vaccine. So we're not even changing the concentration of formaldehyde in an infant's blood when we give them vaccines. Mercury, also found in some vaccines. This has been used as a preservative as well as an antimicrobial, so preventing things from potentially growing in multi-use vaccines, which aren't even really used anymore. But we now know that mercury is found in the similar trace amounts in breast milk that infants are receiving as though they would have seen in vaccines. Also, most vaccinations in the US have now phased out mercury. Antibiotics. So sometimes there are trace amounts of antibiotics in vaccines. It's antimicrobial, so again, to just keep these things sterile. Oh, and I should mention that in terms of antibiotics, they don't use penicillin, or if other antibiotics start showing like an increased allergy rate in the population, they make sure that those are not in the vaccine. And finally, the last most common vaccine component is egg protein. So certain vaccines, including the influenza vaccine, are created in chicken eggs. And so what happens is they try to get all of that egg out when they purify the vaccine, but sometimes they don't get it all. And so with this particular egg protein, that's why if you've ever gotten a flu vaccine, you've probably been asked, do you have egg or poultry allergies? I don't know if you've ever, you should be asked that if you're not. It's because some people do have allergies to eggs. So we want to try not to inject people with things they're allergic to. These are the main components, at least in my kind of limited conversations with people. These are the things that they tend to be most worried about in vaccines. So vaccine efficacy, I'm gonna probably, I can go through this rather quickly. So the WHO estimates that annually, so per year, vaccines prevent 2 to 3 million deaths currently. There are many, many examples. I will just give you a few actual examples of showing you the statistics and I even have some graphs showing you the efficacy of vaccines and preventing diseases. So in 1921, more than 15,000 people died from diphtheria, which diphtheria is a respiratory bacterial infection. And after the vaccine was implemented and used widely in the US, we've actually only had 2 cases of diphtheria between these 10 years, 2004 to 2014. So we went from having 15,000 people a year dying from this to now only having a handful of cases in 10 years. The year before the rubella vaccine, which is part of the MMR, was introduced. And rubella is also called German measles, if that sounds familiar to any of you. It usually is a pretty mild infection unless you're pregnant. Rubella was one of the leading causes of severe birth defects and death in infants. So 12.5 million people were infected just in that year, 1964 to 1965. It caused 11,000 miscarriages, and 2,000 babies died due to severe complications after birth. Since the rubella vaccine has been used, very few cases have now been reported annually since 2012. So again, a handful of cases. Here's some graphs to kind of depict basically the same story. This is a polio vaccine graph. So polio is extremely contagious and can be extremely devastating in terms of complications. It's actually still an issue worldwide, even though it's no longer an issue in the US. There were 2 vaccines introduced, and you can see that the number of reported cases in the thousands went drastically down after the vaccine was introduced. This is reported cases of polio, and this is in the US. Same is true for measles. Highly contagious. Introduction of the vaccine, the MMR vaccine, and the cases went down. This was actually, the measles was declared eliminated in the United States in 2000. And I have asterisks there because that status has now been removed because measles has come back. So what is the point of this? The vaccines, many of the vaccines are actually highly effective at providing a memory immune response capable of protecting us against the actual infectious agent. So vaccine safety, you probably know this, but sometimes I feel like I just need to remind some people, depending on who my audience is that vaccine safety, remember, is highly regulated and continuously monitored, even in vaccines that have been around for a really long time. This is done by multiple bodies, both governmental and international. Side effects are indeed possible with vaccine use, definitely. Usually these are really mild. Some people will get redness, rash, pain at the injection site. Like when I get the tetanus vaccine, my arm always hurts for like a full day, you know? Some people will get fever. Those are considered mild. And if you want to think about this, is those side effects are actually usually a sign that your immune response is working. So you're like, hey, it worked, hopefully. There are instances of rare, severe side effects. Usually this is actually an allergic reaction to something that's in the vaccine, egg protein, particular antibiotic, so on and so forth. It very rarely causes death though, because these types of allergic reactions happen extremely rapidly and usually are still happening when the patient is still in the clinic or very close by and can receive the treatment they need. Usually involves an epinephrine pen. Millions of vaccines and outcomes are monitored every year. And the risk of one of these severe reactions is about 1 in a million. In fact, I was looking to try to find better statistics, and the CDC actually says that calculating the risk of severe reactions is almost statistically impossible because the risk is so low. So this VAERS monitoring I mentioned, physicians, when they give vaccines, are encouraged to report anything and everything that might happen after giving the vaccine to the government. There's a special team of scientists, statisticians, that will look over those reports weekly. And so an important point here is that coincidence does not actually always equal causality. So like, let's say I get a vaccine and on my way out, I trip because I am clumsy. I am actually very clumsy, and I break my arm. The physician would most likely report that I broke my arm after I got my vaccine. Now, if this team now, during their weekly monitoring, notice that there's an increase in the amount of people that are breaking their arms after the vaccine, then they will take action. They'll probably halt the use of that vaccine until they can figure out if there's actually something going on. But just as a reminder that coincidence does not always, or even usually, equal causality here. And the benefits to risk ratio is really important to keep in mind. It's kind of a visual way of representing what I've mentioned already. So if you look at diphtheria, which is that nasty bacterial respiratory infection, versus the DTaP, that's what the diphtheria vaccine is in, there's actually a 10% mortality rate with diphtheria. So if you get diphtheria, you have a 10% chance of dying. With the vaccine, you have a 1 in 1 million risk for a severe reaction that most likely will not kill you. So that's what they're looking for when they release a vaccine and also continuously monitoring it, is they want to make sure that the benefit to risk ratio is huge. They want it to be way more beneficial than risky. And if that starts to change at all through their monitoring, then they will look into it. Okay, I think I'm mostly done. I am just going to leave this here, and if anyone wants to discuss vaccines and autism, we can talk about that in our discussion. And I will tell you about the millions of children that have been monitored and found to have absolutely no association with autism. I can also tell you about this initial study by Andrew Wakefield and how flawed it was. So if you have questions about that, you can ask me after. All right, so I've been very pro-vaccination, you've seen, right? Like, hopefully that's not a surprise. But there definitely are vaccine limitations. So some at-risk populations cannot be vaccinated. We talked about some severe immunodeficiencies, for instance. Vaccines aren't safe for them. So immunocompromised people. Infants cannot receive certain vaccines in their first year of life. Those are just some examples. Most vaccines are not 100% efficacious. The influenza vaccine is notorious for not being, even some years, very even close to 100% efficacious. Some people ask, why don't we have vaccines against everything? And that would be great. It's just sometimes really hard to make new vaccines to some things. Scientists have been trying for decades to make a vaccine for HIV. And just due to the virus itself, it's really difficult to get a protective vaccine. Same thing with malaria. A malaria vaccine would be spectacular, but it's been really difficult. There's actually a financial risk in terms of the pharmaceutical companies. They don't make a lot of money with vaccines. Vaccines are quite cheap. So for example, I think the DTaP vaccine, I think the pharmaceutical company gets like $30 for a vaccine. Whereas in some of the other types of therapies, So a lot of the new cancer type therapies, the immunotherapy, those can be like hundreds of thousands of dollars per year per patient that the pharmaceutical company can rake in. So there's definitely that side of it, unfortunately. And finally, worldwide dissemination difficulties are a real problem too. It's hard to get the vaccine out everywhere it needs to be for various reasons. So vaccine hesitancy is this new thing, the new term. It's now a top 10 threat to global health, according to the WHO. The number of unvaccinated kids has massively increased in the last 20 years. It's quadrupled. And there's a lot of people who like to think about why that is. It could be complacency. My generation, we don't remember what it was like when measles was rampant or when diphtheria was everywhere. So it's hard to remember why vaccines are necessary. Inconvenience, people don't want to get vaccinated. And then the biggest one probably is the lack of confidence. Lack of confidence in that they work, that they are necessary, or that they're safe. So I'm almost done, I promise. My last few slides are about why do we still vaccinate though? And that really has a lot to do with protecting others. So you've probably heard of this term called herd immunity lately too, right? So herd immunity was originally developed for vaccines. And basically what it says is that if only some people are getting vaccinated, which in this picture here is showing yellow, these people are vaccinated, then if we get one guy here in the middle of the crowd who is sick and contagious, he can infect a lot of people because there's not a buffer. There's only a few protected people here. So most of the crowd here is now susceptible or exposed to this contagious person. So what if we flip it around and say, okay, now most people are vaccinated. The same scenario, we've got this contagious sick guy in the middle, except now most of the people are yellow, they're vaccinated. So he's coughing and hacking, spreading virus. But now we're infecting a lot less of the unvaccinated people simply because we have this buffer of protected people that will not continue to progress the infection to others. Diseases also have not disappeared. It's estimated that even with the current vaccines we have, that 1.5 million people or so are dying annually from diseases that we can currently vaccinate against. Diseases also can return. And I'm just going to give you this one example, measles. So this is now looking at number of cases in the US. Remember, it was declared eradicated in the US in 2000. And then especially in 2019, last year, there were outbreaks of measles. And these outbreaks were mostly occurring in populations of unvaccinated people. And so they had to rescind that eradicated, or not eradicated, I don't remember what word I used, whatever. They had to rescind that status because it came back. The interesting thing is that in 2020, I just looked this up a little bit before this meeting, there have only been 5 cases of measles. Anybody guess why that is? Not because people are getting vaccinated. It's because we're all stuck at home. We can't infect each other. We can't infect each other with COVID. We can't infect each other with measles. Yeah. So I guess that's good. I'm not going to go over this example. Okay. This is the last slide. And it's just talking again about vaccine science. So there's still ongoing research into vaccines. So oh, sorry, this got kind of cut off. But so for current vaccines, even vaccines that have been around for years and years, there's still research about how to improve them, make them safer, more efficacious. How do we get them out where they need to go? New vaccine components to put in. Are there safer adjuvants or preservatives we can use? Right now, new vaccines, at least before COVID came along, they were looking into Zika, Ebola, and then also oncogenic viruses. Oncogenic means can cause cancer. So those are what they were focusing a lot on, was to develop new vaccines. How about what we have going on right now? So the first thing I can tell you is that we do know that there is a pretty significant immune response to the virus. And I can put this link in the chat in a minute, just so you can go to this website if you want to. But it's a really great depiction from one of the best journals out there, Nature, about what we know so far about innate and adaptive immune responses to the virus. We know that an immune response happens. We also know that in a lot of the most severely sick patients, including ones that die, they seem to have an overreactive immune response, meaning the immune response might be doing most of the damage, including a cytokine storm. What that means is that for some reason, the virus is causing massive damage and inflammation, and the virus and the immune response then responds kind of accordingly. So like the larger the response from the pathogen, the virus in this case, the larger the response from the immune response, and so on and so forth, and so on and so forth, until finally tons of cells are activated of the immune response. They're all spitting out cytokines, which is basically how inflammation happens, and then it's just too much. So we still don't know a ton about what's happening. You know, this is science. You're seeing science happen, you know, quickly. But we do know some. And we do know that there are many vaccines right now that are in various stages of clinical trials. So the last I looked, there was 135 worldwide, 135 different vaccine types. They're all those different types I showed you. There are inactivated subunit, inactivated whole, there's attenuated, like there's all kinds. I think the furthest one along is at phase 2, phase 3 right now. It usually takes years to develop and get a vaccine into the public. And the world, the scientists of the world are pushing to get this thing out in a year. I mean, it's, as a scientist, I actually have goosebumps right now thinking about it. I cannot, they are pushing so hard. I mean, if they get it out in 2 years, it's going to be amazing. So, but I found a vaccine tracker that lists all the different vaccines and where they are in the clinical trial, and they update it daily. So that's what that website is. So I'd be happy to give that to you too if you're interested in looking those two things up. So I know that was kind of long, but I thank you for bearing with me. I would be happy to answer, you know, any specific questions that you might have, but then also maybe we can do those first, like if you have some specific questions about what we just talked about. And then once those are done, we can, you know, have kind of a larger discussion about bigger picture things if you're interested in that. So you can unmute yourself if you want, or you can chat in the thing.
Well, Kristen,
Mhm.
I think one of the things that I gave a talk on last year to HASP was on the immune responses, the immune diseases that I, as a rheumatologist, have been seeing from some of the new cancer therapies, which shows that good things can have bad side effects as well.
Yeah.
The other thing I want to mention is that this cytokine storm, the news media has been calling it this mysterious new disease. We've been seeing this in infants before, called Kawasaki's disease. It's the same immune process.
Yeah.
It's not anything different. It's not a mystery at all.
No.
So
Yeah,
just
I would
appreciate
agree.
the comments.
Yeah, no. Thank you for your comments, and I agree with you completely. Cytokine storms. I mean, that's basically what is happening even in anaphylactic shock.
Yes.
Is a type of cytokine storm. I mean, this has been around for a long time, and the media enjoys, you know, pretending like things are new to scare people. And then about your comments with the cancer therapies, yeah, that is really interesting. Unfortunately, not surprising, but yeah,
No. It's of course because it's affecting the T cell.
yeah, yep. Thank you.
Thank you.
Other questions?
I think, let me add one other thing, Kristen.
Yeah.
Your talk should be put on a disc and given to every pediatrician. They can play it to their non-vaxxers, because I just heard a non-vaxxer yesterday tell me that everything was due to Tony Fauci and not due to the president, and the president should not be blamed. So I think your tape should be played as a pediatrician to try to convince the non-vaxxers. It may not work.
Yeah, thank you. I'd be cool with that. I will mention, because one of the questions we had on the chat just really briefly is like what message I have for people who are against vaccines. It is this. I developed this talk, it's slightly different, but I developed this talk to give at a community talk. It was actually at a bar, and there was a big population of anti-vaxxers there. And I actually ended up having to leave out a different exit because they were trying to block me from leaving. So I've definitely given this talk to anti-vaxxers, and I don't think I changed anyone's mind, but I feel like it's kind of my duty to at least talk about what I know in a way that's hopefully accessible. So.
Well, doesn't alcohol kill bacteria?
Oh yeah, kills COVID too. COVID's a wimp. So.
Bar, that's a good place to treat it.
Let's see. What is the basis for antiviral compounds? I see in the chat. So yeah, so depending on the antiviral compound, they work very specifically usually. So some antiviral compounds that you'd be given as a drug for a certain virus might prevent the virus from actually getting into a host cell. They could prevent that step. Some different types of drugs will mess with the virus when it's actually in the host cell itself and not let it do something with its DNA or whatever. Then there are even other drug compounds that will prevent the virus from leaving the host cell to try to infect other neighboring cells. So I don't know the specifics too much about this particular drug compound, like what it actually does, but my guess is so Ebola and the SARS-CoV-2 are two very different types of viruses. So where some types of drugs work really well, for preventing virus X from getting in, that same drug might not work as well for letting virus Y from getting into a cell. So that's how a particular drug could potentially be beneficial for one type of virus, but not another. Let's see. So yeah, okay, that's a great question. So in the chat, there's a question that asks, what is the significance if a person is told they have very, very few memory cells? It kind of depends. That's like my answer to everything. It's a kind of political answer, I feel like. So for instance, infants have very, very few memory cells, right? Because they're brand new. They haven't been infected with anything yet. So they still have lots and lots of T cells and B cells that can become memory cells, but they have to go through something first, whether it be an infection or a vaccine, right? So in some instances, having few memory cells isn't necessarily a bad thing. However, if at my age, I went in and I had very, very few memory cells, that would not be expected and potentially could be detrimental to me. It could mean that I'm no longer protected against the things I've been vaccinated against. It could mean that I am not making memory cells, which would be kind of a deficiency in the immune response. If you think about the graph that we had, maybe you're having a really good initial response, but then for some reason, there could be many, you're not getting a long-lived memory population. Maybe those memory cells aren't living as long as they should. Yeah, so depending on the situation, it could be an indicator of some type of immunodeficiency, I would think. Mm-hmm. Other questions?
I think you've answered all the ones in the chat.
Maybe I don't know if I can. I was going to try to put those websites real fast.
Oh, yes.
In the chat while people are thinking. There's that one. And there's that one.
Perfect.
Okay. Or I can just get out of this too.
Okay. Kim, do you want to wrap it up for us? Other Kim?
Sure, sure. Can you hear me?
Yeah.
All right. So I hope everyone found this informative. As I was saying in the beginning, the timeliness of this was certainly not expected when Kristen and I first discussed the possibilities of this presentation. But Kristen, I think you did an excellent job, and we had a bunch of excellent questions. And boy, let's try to stay safe out there. Thank you.
Thanks. Thank you, everyone, for your participation and your questions. I really appreciate it.
Thanks so much, Kristen. You did an awesome job. Thanks for being with us.
Thank you.
Bye, everybody.
Bye.